Bien, je suis ravi et très honoré d'accueillir ce matin le professeur Andreas Kortenkamp, qui nous vient de l'université Brunell à Londres. Le professeur Kortenkamp travaille depuis, je pense, plusieurs dizaines d'années, une trentaine d'années, sur la problématique des mélanges et de l'évaluation du risque dans le contexte des mélanges. C'est vraiment un des experts reconnu sur cette problématique au niveau international. Il s'est notamment beaucoup intéressé à la perturbation de l'axe androgénique, et je pense que beaucoup de ces exemples seront tirés de ces effets sur l'axe androgénique. Il a réalisé un certain nombre de rapports, et notamment pour la Commission européenne, sur la définition, l'identification, les effets de ces perturbateurs endocriniens, et je lui laisse tout de suite la parole pour une petite heure. Please, Andreas, we are all ears and looking forward to talk.
Thank you very much for this kind introduction and the invitation to speak to you this morning. I'm going to talk about mixture effects. I've called this Bad Cocktails, an introduction to mixture toxicology. This is the mantra of traditional single chemical risk assessment. Protection from mixture effects is achieved as long as exposures to each individual chemical stay below thresholds. Now, to take this apart and to probe whether this is actually scientifically tenable, we have to address two issues. First, are there mixture effects at very low exposures? Is this possible? And secondly, what is the degree of underestimation of real existing risks from chemical cocktails when we just disregard this and carry on as usual with single chemical risk assessment? I will start with the latter point, underestimation of chemical risks. And allow me to introduce a case study which links nicely with what Professor Slama discussed in his previous lectures. Male reproductive health. Declines in semen quality are a concern and have been a concern for decades. Here are the results of one of the largest studies in this field. 100,000 men were investigated. Ignore the red and green curves. Just focus on the blue declining curve here. This shows you the proportion of men with insufficient numbers of total motile sperm. And as you see, over the years, that has decreased by quite a degree. This is an important measure because the fertilization success depends mainly on the number of motile sperm. They have to find the egg. Another measure is total sperm concentration. This is a graph taken from a large systematic review by Levin and colleagues. And you see here a compilation of virtually every study into sperm concentration conducted until 2017. And you see this regression here. Overall, there's a declining trend. This has been a concern for many years, and the researchers engaged in this have warned about this, but it was very difficult to follow up on this because the contours of the problem were left rather hazy, which is where we come in. We know there are non-chemical stressor risk factors leading to a decline in semen quality, but also chemical factors. And the goal we have set, we and in our team have set ourselves is to see whether we can define the contours of this problem, but from a mixture perspective. And a mixture perspective is absolutely essential to achieve this goal. And that's probably why it has been left unresolved for so long. The approach we're taking is mathematically very simple. You have here these, let's see, does this work? Yeah. These quotients, they're called risk quotients. In chemical risk assessment, you make a ratio of the existing intake or exposure to a chemical and divide it by what I call here a reference dose, which is something you think is harmless. That's the limit. And if these ratios for a single chemical approach 1 or exceed 1, risk managers get alarmed and they start doing something. So in mixture risk assessment, we will take this apart later on mathematically, but for now it suffices. In mixture risk assessment, we demand that the sum of these risk quotients for all the chemicals we consider together must stay below 1. Now, what are the assumptions behind this approach are, first of all, that dose addition, I will explain later on, is a good approximation of really observed mixture effects. And the other assumption is that we're not dealing with synergisms. Mostly the effects of these chemicals are all additive. What is the interpretation of this sum of risk quotients if it exceeds 1? We have an exceedance of combined acceptable exposures. What we cannot estimate from this number is a strength of effect. We need some additional assumptions for that, but I want to make this absolutely clear. So in our exercise, this is the largest mixture risk assessment exercise in this area and beyond. So far, we included no fewer than 29 chemicals. They are listed here. These are the dioxin, polybrominated diphenyl ethers, PCBs, acrylamide, butyl paraben, pesticides, and phthalates, bisphenol, painkillers. How did we arrive at this list? We did a systematic analysis of pathways that can lead to declines in semen quality and ask, do any of these chemicals fit this effect profile? Now, very recently, through a fortuitous coincidence of events, we teamed up with the team at the Copenhagen Rigshospitaler, Hanne Frederiksen, Anna-Marie Andersen, Niels Jørgensen, and Niels Skakkebeck. These are the pioneers in research in semen quality. And they published this paper in which they measured in one and the same urine sample this set of chemicals. And this was very precious to us because the combined exposures before we just had to infer from global population data. So we traveled to Copenhagen, did this analysis because it gives us the opportunity to make a mixture risk assessment personal for each individual. And allow me now to take you through a quick series of animation, a journey from the viewpoint of a single chemical risk assessment fetishist. So let us see where this leads us and to what degree we underestimate real existing risks if we don't take account of combined exposures and mixture effects. Let us begin with one phthalate. So every dot here is one individual, one man analyzed in Copenhagen, the urine sample. You see, this chart here shows the higher we are here on this axis, the more complex is the mixture. Because we're looking at one chemical, the complexity is 1 or very low. And along this axis here, we're looking at the combined risk. If people get over this red line here, which is 1, we are in this red zone of combined unacceptable exposure. So let's now watch what happens. So there's no concern. That's the conclusion here. Please note also that's the power of this consideration, the variation in exposure which is behind this. This is more than a factor of, this is nearly a factor of 100. That's to be expected. So every risk assessor will now conclude there's no concern. Absolutely no concern, nothing to worry about, move over, next chemical. And this is how it's done, chemical by chemical by chemical, always no concern, or very often. It's like the Italians call it salami slicing. Here is the sausage, thin slice, oh, nothing, whoop, next one, and so on. And at some point, the whole sausage has disappeared. That is the philosophy of single chemical risk assessment. Now, here we're adding one phthalate. What you see here is the complexity of of this mixed exposure goes up, as is to be expected. This is 2, which means these individuals up here are almost equally exposed to these 2 phthalates. Others down here, there's 1 phthalate that dominates their personal exposure. So every dot, 1 person, 100 people. So now let's go. So 3 phthalates. You see the movement already, we're moving towards the right. But still no concern. 4 phthalates, there's probably 1 individual just over the line, but overall no concern. 5 phthalates, now it gets interesting. About 12, maybe a quarter, 20% are now over the line. Okay, this is where the field stops. The field is obsessed with phthalates. We can conclude, okay, there is some concern, but now watch what happens. Bisphenol F, 50% over the line. Watch also the complexity of exposures in some individual rises. Okay, we add bisphenol S, the majority is over the line, and also quite complex exposures. There's still some individuals, that means this person is very highly exposed to 1 chemical. That's why they're far too, but already look at those, this is 10-fold over the acceptable level, which is this one here. And now we are kicking off. Bisphenol A and paracetamol. Look at this. So these are all 9 chemicals jointly measured in these urine samples in Copenhagen. No one is to the left of this line. All individuals experience unacceptable exposure, some even as high as 100-fold over the line. That is the zone where, with equivalent doses in an animal experiment, we would begin to see effects. So I want you, now we haven't stopped. We now feed in the 20 background chemicals that weren't jointly measured. You see here, I can go back. You can see here. Yeah, that's what happens. Of course, the complexity rises. So what does that mean? Everyone is over the line, according to this estimation. Safety margins are exhausted. And some people approach doses associated with effects where you begin to see effects in laboratory animals. You now want to know what is the picture, what chemicals are actually behind this, what are the most important chemicals. And this is also the power of mixed risk assessment. We begin to see the contours of the chemical exposome that leads to those effects. What this graph shows is all 29 chemicals, the risk quotients now arrayed in ascending order. We see here these chemicals there don't matter much at all. Here we begin. Yeah, so up to this point here, the combined exposures to all these chemicals up to this point are below the line of 1, so you can say fine. Now it gets interesting. This phthalate pushes it over the line, followed by bisphenol F, S, the dioxins, paracetamol, that's a surprise, among paracetamol users, expectant mothers using paracetamol in this window, end of first trimester, beginning of second trimester, increase the likelihood if they bear a baby boy, of the baby boy having higher risk of non-descending testes and probably also poorer semen quality. And here is bisphenol A. So this is the median risk quotient among these people for bisphenol A. Massive driver. This chart is very useful for risk managers because it tells them which chemicals can we target to reap maximum effect. Obviously, bisphenol A, followed by paracetamol. Women should be advised to be careful with it. And dioxins, and you see, and then all the other bisphenol. The other take-home message is, even if the individual risk quotients of all these chemicals were 1, i.e. in a single chemical risk assessment acceptable, we would have a mixture problem. You can see this immediately. So the risk quotient here for dioxins is about 1, but it's already over the line. You can add this and this. We would still be in the zone of unacceptable exposures. The implications of this are that currently, that's the truth, in the European Union there's no protection of the general population from mixture risks from combined exposures. Single chemical risk assessment, I think this little case study shows it very clearly, massively underestimates what's going on. And even a consideration of certain subgroups of chemicals, like with phthalates, which everyone looks at the moment, would underestimate the risk. That is not enough. We need to widen the net. So there are other chemicals, chemical exposures which probably make this picture even worse. We couldn't take into account air pollution. Perfluorinated chemicals are probably contributing as well. But for various reasons I won't bore you with, we could not take this into account. The other conclusion is that the limits, the health-based guidance values for individual chemicals are too high. We cannot manage this problem without doing something about the individual limits of the chemicals. They probably should all be going down, and that's a very interesting discussion currently in the European Commission and beyond, whether we should introduce an additional factor called mixture allocation factor or mixture assessment factor to lower the limit values for all chemicals. Right. Let me switch gear. If any of you have any questions at this point, I'm very happy to take questions, but okay, that's not the case. So how this work, this case study I've shown you, has been done on the strength of decades worth of experimental research, both in my lab and in collaboration with other people. Numerous EU-funded projects were behind this. And I'd like to show you something now which brings a bit of order into this seemingly complex problem. The prediction of mixture effects, that's the philosophy we have been pursuing. We wanted to know, is it possible to accurately predict combined effects when you know the toxicity of all components in the mixture? How can we establish this? And this is also a seemingly simple question, what is synergy? But this is a very thorny one, and I'll go into this as well. What is synergism? Let's begin. Common ideas about this, you add effects. You've seen it in Professor Slama's presentation. 2 + 0 is 5, so more than additive. Many people think that's synergism. Effects stronger than the most toxic chemical in the mixture, and so on. But the key point to consider is synergisms are detected in relation to an additivity expectation, to a calculation of additive effects. And synergisms are diagnosed as effects stronger than additive. Which now boils down to the question, what is additivity? And let me remove one myth right from the start. The idea of additivity in mixture toxicology has nothing to do with adding up effects. In fact, we're adding up something different, or we're multiplying effects, as you will see in a minute. So, but still many researchers, and I see many papers published, they're very poor, think that additivity is defined by adding effects of single mixture components. And this is the fallacy and the problem normally faced by, let's call it novices or theoretically underexposed people in this field. Look at this example. We have, this is the typical beginner's experimental design of a mixture effect. You have chemical E1, you measure the effect in blue, the next one E2 in yellow, and now at the same doses we're putting E1 and E2 together, and we expect, the naive beginner expect the effect should now be this plus this. And then they go away, do the experiment, and they see the effect is that. And then they lose motivation. They say, oh, this is so boring, it's antagonistic. Right? And then they give up. But let us now open the can and add some information. This is a hypothetical example. Let us assume the real dose response relationship of the first one, E1, is this, and the tested dose is this. So here we have that effect magnitude. And let's assume for the other chemical, the curve is this, and the tested dose is the yellow arrow. Now, you see perhaps the expectation of that if you put this plus this together, the effect should be the sum of this plus this, is totally biologically impossible because both curves level off here at 1. So the simple adding of the individual responses does not take into account that biologically a maximum effect is only possible up to 1. So we see the naive adding up of effects in this area doesn't lead anywhere. So what is a better approach? So how can we do this more reliably? There are two concepts. One is called independent action and one concentration or dose addition. They are both good approaches, theoretically legitimate, but mathematically totally incompatible. So I'll right, this is my market in London, and imagine you stand in front of this stool and have a handful of pebbles and want to throw these pebbles or nails and smash up all these eggs. Okay. Independent action allows you to calculate an expectation about the expected effect of a mixture of successive application of throwing a pebble and nails. Let's start with pebbles. Let's assume that one dose unit of pebbles breaks 90% of the eggs and 10% are left. And let's assume one hit always breaks one egg. And yeah. At the start we have 1,000 eggs there. After this one dose unit of pebbles, 0.1 times 1,000, i.e. 100 eggs are left. Okay. So to calculate the effect of 2 throws of pebbles, we multiply this. So, yeah, so again, if you throw another dose unit of pebbles, you would be left with 10 eggs. Yeah, that makes sense. So here you begin to see the idea of effect multiplication. Nails, we assume nail break, somehow they're less effective. 50% after one throw of nails, this one dose unit, we're left with 500 eggs and so on. And the combined effect of pebbles and nails thrown in sequence is now, you have guessed it, just we multiply this and we formulate the expectation 50 eggs are left. So therefore this formula, this multiplication of effects, very good, and there's experimental evidence for this, that this works. For decreasing those response relationships, it's this formula, and for increasing, it is this. Now, what about the competing concept of concentration or dose addition, which is actually should be used as a default? There are very few examples where independent action really works. Here we are doing something totally different. We are not thinking along the effect axis, we have to think along the dose axis. And the idea behind this is that chemicals in a mixture contribute to the joint effect in proportion to their dose, without interfering with each other's action. So we're not adding or multiplying effects, what we're doing is we're adding doses. How does this work? This should be quite familiar from the way dioxins are risk assessed. So imagine this is a melange of dioxins or other chemicals. They all have these dose-response relationships. I want to calculate the joint effects of 1, 2, and 3. Here is the curve for 1. I know it's present at this concentration in the mixture. I read this off and project it onto a reference chemical. In the case of dioxins, it's 2,3,7,8-TCD. And read off the equivalent dose of my reference chemical, which is that. It's a fairly straightforward exercise. I do the same with chemical 2 and 3, and then, therefore, the name dose or concentration addition. I now add up literally these concentrations here The answer is here. It's a logarithmic scale. Go up and read off the effect. Voila. Concentration addition. That's why this strange name. So how does this work in a real experiment? We've really done it multiple times, but we set ourselves the goal of examining the combined effects of 3 chemicals known to feminize male rat offspring of mother rats which were exposed during gestation. We did this in collaboration with a very good group at the Danish Technical University in Copenhagen. We looked at changes in anogenital distance, which is a measure of anti-androgenicity. It's used to sex rats. Normally it's longer in males, shorter in female. And with this, I will show you in a minute, you totally feminize male rats. So here we are. We started off with recording the individual dose-response relationships for these 3 chemicals. Vinclozolin, a pesticide, flutamide is a drug, and prosimidone, another pesticide. And we knew all these chemicals have in common, they antagonize the androgen receptor. And you see here, you can chemically totally feminize these male offsprings. At this point, our colleagues in Copenhagen didn't know whether they were handling girls or boy rats. It's so drastic. So these dose escalation experiments. So we used this information to make a prediction about the joint effect of these 3 at a given mixture ratio. And then went away and tested the prediction. And here's the outcome. Here you see the experimentally observed data. I should add, the green curve is what we calculated according to dose addition or concentration addition, and the blue one is for independent action. In this case, it often happens, the 2 models produce virtually the same predictions. But look here, we were so fearful. This experiment took 3 years to do. And we were worried, would this work? We thought this is quite a complex arrangement. We couldn't test everything in parallel. But the agreement with both additivity expectations was shockingly good. And this is now a classic paper. We conclude vinclozolin, flutamide, and prosimidone add in an additive fashion. Now, to synergisms, had we seen effects here in this zone, the observed, obviously stronger than predicted, that would be a synergism, and over here, that would be an antagonism. Here's an example of a synergism we saw in the same kind of experimental design, but looking at a different endpoint, genital malformations in the penises of the rat, which is similar to a condition called hypospadia in humans. And you see here, this is the window of additivity expectations based on the potency of the chemicals in the mixture. Vinclozolin, finasteride, procravas, and the diethylhexyl phthalate. But look here, the observed effects. Already, where all additivity expectations say nothing should happen, we see a considerable effect, and look at here. So that's a synergism. I mentioned at the beginning that wrapped up in all this is the thorny question of mixture effects at low doses. And does all this still work with low doses? What is a low dose? A thorny problem in toxicology, easily skirted over by most toxicologists. Right, here is an in vitro experiment in which we used these MCF7 cells and did a dose or concentration escalation experiment with an organochlorine, doesn't matter what it is, and we measured. This is normally you don't see finely spaced dose response relationships of this kind, and this is a high throughput assay. We played with the power of high throughput assays and really, as you can see, tested to destruction this low dose range. Okay, so right, I ask you, where's the threshold? Can you see a threshold? It's not trivial. So the threshold is a dose with zero effect. But the regression model we used here has no intersection with the zero line. So it goes asymptotically, so there is no threshold which we can derive mathematically. The problem is that even untreated controls produce this noise. Yeah, that obscures quite a lot. So there are pragmatic ways of dealing with this problem, which is called a no observed effect concentration, or the other way would be to interrogate this regression model and ask what are concentrations associated with a 1% response is here, or a 5% response. So you see here. This is not trivial in a mixture experiment context, because can we be really sure in this zone that the effect is 0 or nothing? Can we ignore this? If we added up loads of chemicals, all in this range, what would happen? I can tell you what happened. We tested it. It is dose additive, and it will produce a very significant effect. It only depends on the number of chemicals you put together. If this number is sufficiently high, you will see an effect. So we busied ourselves with making decisive low-dose mixture experiments. If you want, this is in detail described in this paper of mine. Now let us look at some theory expectations in this area, and that is why you will see in a minute why conventional toxicologists and the apologists of environmental pollution prefer independent action as the default. Dose addition, the theory behind this, means that we expect mixture effects if there are sufficient numbers of chemicals, even at doses below 0 effect levels. Everything, if there's enough around, everything will add up. In contrast, independent action theoretically expects that mixture effects will not occur if all chemicals stay below the 0 effect level. And you see here why normal risk assessors like this. So we did this, we tested this out, and I'll show you the results of some decisive experiments. But we need to avoid, I'll skip this, we can see. So here is one study which we did, not endocrine disruption, but genotoxicity. Benzimidazole pesticides, they make a genotoxic lesion called micronuclei. You see here, these are normal nuclei of normal mammalian cells, and this is stained with a fluorescent dye that catches the DNA. You see here things like that, that's what I call micronuclei. This is material expelled from the main nucleus and residing in the cytosol of these cells. So this could be broken chromosomes or entire chromosomes kicked out. And these benzimidazole pesticides work by interfering with the microtubuli that pull the chromosomes apart in cell division and divide and distribute them to the daughter cell. So they disrupt this, and then micronuclei occur. In this case, we used regression models with a threshold parameter. So we used various models, and here we introduced a threshold parameter because we wanted to test the independent action assumption. This is what we got, 7 benzimidazoles. These dose-response relationship shows you as the frequency of micronuclei goes up with increasing concentration. And highlighted by vertical arrows, I have the kink in the regression model. So we use this as estimates of a 0 effect level. And then what we did to test the assumption, we took from each of these benzimidazole pesticides these doses here and just put them together, one on top of the other, literally, and then measured. And this is what we got. First, this is the expectation according to concentration addition. This is the expectation according to independent action with a kink. That is the dose precisely where we put everything together from the kink from the previous slide, and here's the effect. Independent action expects the effect to be there. conclusive evidence that that according to concentration addition, we can get mixture effects if we combine everything at threshold doses or even subthreshold. Here, the individual concentrations of all the players in this mixture are below the threshold. Here, you see that. And mathematically, had we had the resources to include more pesticides like that, we would have got an even stronger effect. So, low-dose mixture effects, the assessment dilemma. According to dose addition, as I've said, combination effects at subthreshold levels are expected and are empirically confirmed. We've done similar experiments of this kind. But this must not be misunderstood. It materializes only if we have sufficiently large numbers of chemicals in the mixture. You will not observe this with just a binary mixture. Absolutely unrealistic. So, the assessment dilemma a mixture risk assessor faces now is, if you want to make valid statements about combined risks, you need comprehensive data about the exposure scenarios. And this is what we don't have. You need to be sure that you're considering together all relevant chemicals. And that is a big uncertainty. In independent action, we also have an assessment dilemma. The validity is confirmed in studies with algae and bacteria. We recently also did it in fish. But the requirements for strict independence are rarely met in practice. You have to really make a mixture, often artificially, of chemicals that strictly act in an independent fashion. But we have here another assessment dilemma. If you remember, if that applies, we need certainty that all exposures are at zero effect levels. And that's impossible because you cannot easily define what the zero effect level is. You know all these approximations, no observed adverse effect levels, etc., etc. They are only approximations. They are not zero effect levels. Every biostatistician will know this. And here we are, all of a sudden, mixture toxicology exposes some quite significant theoretical problems. So, let me end. I thought I cannot conclude this little presentation without telling you something about synergisms, proper synergisms. You've seen one already. Here's a very interesting paper by Belden and Leidy. What they did was measured the mobility of fish, which they exposed to two pesticides, chlorpyrifos. It's an organophosphate, and that inhibits acetylcholinesterase, and that impedes neurotransmission and leads to muscular paralysis. So then the fish begin to have difficulty swimming. And then a pesticide, this is a pyrethroid pesticide, S-phenvalerate. It blocks voltage-gated sodium channels, and this prevents the repolarization of nerves and leads also to paralysis. So these two have made a mixture of these two pesticides, all properly done on the basis of single chemical dose response analysis. Wonderful paper. And here they produce the two expectations. This is independent action, and this is concentration addition. So that's what they thought the observed effect should be like. They are here. Shifted to the left towards lower doses, a clear synergism. The experimental error, it wobbles here a bit, is beyond this expectation here. Clear synergism. What happens? Why does this happen? Both chemicals affect the mobility of fish by paralysis, albeit through different mechanisms. But why are the effects stronger than additive? This is because chlorpyrifos also inhibits enzymes that detoxify S-phenvalerate. So the result is that we have higher levels of S-phenvalerate in the fish than we would normally have if we applied S-phenvalerate singly. Therefore, the mixture becomes more toxic and the additivity predictions do not work anymore. That's the reason There are many other examples like this. We have some determinants. We know now what determinants for synergisms are. When one compound increases the bioavailability of another, you are likely to have a synergism, or the uptake of another, or if one chemical speeds up internal transport, or induces a metabolic step that toxifies a component, or inhibits one that detoxifies, or if one component enhances the binding at a target site for toxicity, or delays excretion of another component. These are all known and demonstrated determinants of synergisms. We have done a massive systematic review of all the literature. The European Commission wanted this, we've done it. The uncertainty in this area is we understand the determinants, and there are some combinations, especially of pesticides, known to be synergistic, and that is known. And the aim was to see, are we really sure about this? How big is the synergy problem? So we did a massive systematic review of the literature, and in particular reanalyzed papers where the authors said, hooray, we found a synergism, which is a bias issue in the field. Everyone gets very excited about synergism. We reanalyzed this and came to the conclusion these claims are inflated, because many authors do not take into account, when you have these deviations from predicted additivity, that there's normally also a variation in response, and often these synergisms were very small. We detected only very few that really stand up, which is in a way good news, because it argues for default application of this concept of dose addition, which, and now I'm closing the circle, enabled us to do this case study on male reproductive health with semen quality. This is dose addition applied in practice. It works with readily available data, and yeah, we've shown this. So with this, there's still a mountain to climb in the area, but we're really making great progress. And with this, I'd like to thank you for your attention, and again, for the opportunity to present in front of you. Thank you.